Okay guys, welcome back. So in the last video I talked about a simple example in which we took infinite number of resistors and we connected together and we found the resistance. So in this video I will be explaining a new concept in current electricity, which is the potential difference and energy. Now you know what is meant by the potential difference, but you don't know the relationship between the potential difference and energy. So the relationships between these quantities I have been talking so far in mechanics, in gravitation, in heat, everywhere. So another relationship that we can build up is the relationship in current electricity, which is the relationship between the potential difference and energy. You know what is meant by potential energy. Potential difference. You know what is meant by energy. Now, how to build up a relationship between these two quantities? So let's define potential difference first and energy first. So what actually happens is that if I take a point A here, so this is about potential difference. A here, and a point, I'll take some point B here. Point B here. If I take a positive charge anyway, right? Anyway, regardless of the path, so here the work acts as a conservative quantity regardless of the path. Like that, and I'll take the charge of this one to be plus Q, right? Take this one to be plus Q. If I take a plus Q, right, a charge of positive Q or plus Q, the work done by an external agent in taking this unit positive charge from B to A or from A to B is called the potential difference, right? The work done by an external agent. So if we are taking a battery or something like that, the external agent will be the battery. So the work done by the battery in carrying this charge from A to B, right? Carrying this unit positive charge. So this is plus 1 Q. So plus 1 Q, I mean plus 1 coulomb, right? So regardless of the path, whether you are taking this way, a straight line, anywhere, right? Curved one, what it matters is that you are taking from A to B, right? Whether it's something like a zigzag path, a curved path, a linear, a parabolic, anything, right? It doesn't matter the path, you are taking the direction or the way you are taking. You have to take, if you take it from A to B or from between any two points, so you know that the potential difference is measured between 2 points. You take the potential at this point, you take the potential at this point. So the potential difference is the difference of potentials between these 2 points, right? So you know that. So that's a basic concept in current electricity that I also taught in the first video of current series of videos on current electricity. So if you have not watched that video, I invite you to watch that video and come back here. Alright. So the work done by an external agent in moving this positive charge from A to B, unit positive charge, is called this one, the potential difference. So you know that I is equal to dq by dt or q by t, simply q by t, right? I is equal to q by t. So q is equal to now it, right? Q is equal to it, and you know that if you take a unit positive charge from A to B, the work done is V divided by the charge multiplied by the charge. So if you are taking so this for 1 coulomb, if you are taking Q coulombs, between A and B, the work done will be W equals V for 1 coulomb. Then for Q coulombs, the work done will be W equals VQ, or we probably call W equals QV, right? For 1 coulomb, the work done is equal to W. So for Q coulombs, that will be W equals QV or VQ, right? Anyway. So you know that Q is equal to IT and W equals QV. So you can substitute the value of IT in place of Q. So W will be Q, which is IT times V. IT is not it, right? IT times V. So W will be VIT. So W will be VIT. So this is again a very important relationship and a very important equation that you will be finding in potential difference, energy, current, electricity, and what actually happens is you can find a relationship like this. Alright. Now what if some circuit is connected, and if I take some wires to be like this, a resistor to be like this, resistor of resistance R be like this, and when a current of I flows through this circuit, I will assume that the potential difference between these 2 points to be V. So assuming this as an OV conductor or some conductor, we can say V equals IR. So what actually happens is that you can solve it further. V equals IR. So this will be I times R times I times T. That will be I squared RT. So that will be I squared RT. And since V equals IR, I is equal to V by R. Assuming R is not 0, right? So W is also equal to VIT, in which I is equal to V by R. So that will be V times V by R times T, which is V squared T divided by R. So this is all I equal to VIT. So this is an important relationship again. W equals VIT, this is equal to I squared RT, and this is equal to V squared T by R. Alright. Now if you connect this, you can see in electric circuits, if you are using some computer or something, right? Electric fans are installed, right? If you are using some other electric appliance also, there are some cooling methods, right? Some cooling methods in which high heat is generated to protect the appliance. So what it actually happens is that if some heat is generated through this appliance, the heat, assuming that there is no heat loss to the environment, you can say that the total energy or the total work done, the total energy dissipated to the environment or dissipated is equal, right? Assuming there is no heat loss, the total energy dissipated or the total work done is used to generate heat, right? So the total energy generated is used to generate heat. So you can write like that. So the total, since the total energy or the total work done is used to generate heat, you can substitute H in place of I. So H also is equal to I squared RT. It is also equal to V squared T by R. And is also equal to VIT. So if you connect some appliance through a potential difference of V, and if you send a current of I through a time of T, the total heat generated in that object will be VIT. So this is also sometimes called the Joule's heat, right? Joule's heat or Joule's law. So in the next video I will be talking about some other concept that can be derived from this equation. So in this video I talked about what is meant by the potential difference, how we can define the potential difference, what is the relationship between the charges, the current, using the time it takes the charge to take the current, and what is the relationship between work or energy and the potential difference using the current and time. Then we derived using V equals IR what are the other possibilities that we can take, and finally we equated the work done or the energy that is used in this taking these charges to the heat generated, assuming there is no disturbance to the heat. Heat remains the light energy or sound energy or something like that. We took the total work done to be converted